Okay, now that we know how to make a very simple coil like this, um, how we can simulate it, how we can find out, for example, what is the amount of the inductance of this. To do so, we have to define an environment so the simulator can start calculating the Maxwell equations inside this environment. This environment can be air, can be water, can be many other things, but most likely it's air or vacuum. But I'm gonna go with the air, so it's because it's more likely that this coil is in the air, especially if it's going to be used for wireless power transfer. So what I'm going to do is I'm going to go ahead and create basically a box, and this box is going to be large enough that gives our coil a good degree of freedom, and then when you calculate the Maxwell equations inside that, you have quite a good amount of accuracy, as if it's inside an infinite large area without having any boundaries. So it depends how large you want to go, how accurate you want to be. You have to make it larger and larger. So in this case, I'm going to go and make it not very large because I'm going to do some simulations and have a good fast results. I'm going to go and select the first point for my box, and this first point can be anywhere you want, but I'm going to make it very close to our terminal. So I'm just going to put a point here and draw the box. It's not going to be very big, but I think that's enough, and then give it some Z content. Now if you go to the box, let's call the box air. Okay, it's air, and for the sake of that, let's color that like a blue, light blue, so it's air. And also, since we are there, let's right click on that and assign a material and call the material that is air. It's in the Maxwell, and then press OK on that, so it's this type of air. So this is all good, and now I'm gonna go and rotate this environment and see what kind of box I designed. Whoa, that's pretty big. So what I'm going to do is I'm going to go press on this create box and say, okay, the first point, the minus x, is going to be the width. As you can see here, if you follow up the previous tutorials, this coil is going to have a width and a length. So the x value, the first point that I clicked, is minus width divided by 2 plus some values. So let's, instead of minus 5, let's call it minus width alone. Okay, so it's twice this distance, so it's going to be from here to another distance like this to here, which is good enough. And the y of that is, if you remember, it was 1.3 minus actually it was 1.3 millimeter, so that's going to be the same for this case. And the x of that, I'm gonna go down for, I don't know, whatever depth you want to put. I think minus 4 millimeter is good enough for our case. And now I'm going to do is I'm going to go, and for the x value I'm going to say from minus width go all the way to plus width, so it's 2 width for the box. Probably I have to put the multiple sign, and then for the Y I'm gonna go all the way up to, I don't know, 2 length maybe. That's not that bad. 2 times of the length. Did I put the word 2? No, okay. Number 2 is there. And the Z is crazy high. I'm gonna call Z to be some arbitrary values. Let's call it minus 4 millimeters down, so it's 8 millimeters, so it's minus 4 down plus 4 up, something like this. Okay, so as you can see, the ports are touching the air, and that's necessary for many of simulations in the Maxwell, that the ports that you are defining has to be connected to the boundary, and the boundary here is the air. Okay, so now I define the boards like that, and I'm gonna go. One thing that you can do is you can click the air box, whatever you design, and give it some transparency. That's one way to get rid of the fact that you saw that. The other way is you can go ahead and click the air, even if it's, you know, relatively good amount of transparency, you can leave it like that, and then go ahead and say, you know what, I don't want to see this guy right now. I know that it's there, and I know that you are going to model it, and I know that you are going to solve electromagnetic simulation inside it, but I don't want to see it. So get rid of it. Okay, so it's not going to be buggy anymore around you, but it's there. Okay, so if I go click on the eye, you can see that the air is not visible. If I check it, it's visible. If I uncheck it, it's not visible. I prefer to be not visible, so we can do whatever we want to do after this point. I'm gonna rotate this, and now that we define 2 ports as this 2, I'm gonna go and say, you know what, I'm gonna select the faces. One way to do that is right click and then go on the select face, or simply press F, one of these 2. I'm gonna select faces, and then I'm gonna go here and click on the first polygon, and then I'm gonna right click, and then I'm gonna go to assign excitation, and then I can do many excitations, but in this tutorial I'm gonna give you a very simple one, which is actually it's not there. Simple. Okay, the reason that it's not there is because I'm going to do a kind of a simulation that is not by default on the Maxwell. So you press on Maxwell 3D, and then you go on solution type, and then where in this menu you go on the under the magnetic type of simulation, you go and select magnetostatic. So the magnetostatic simulation gives you a very good frequency based characteristic of inductance, capacitance, you know, you name it, B, G, E, all this kind of fields, and it's pretty good. But when you go on the transient, it's going to simulate based on the transient time. It's more accurate, it will take more time, but if you just want to know the characteristic, that, like, you know, the electrical characteristic of your structure, you better go off with the magnetostatic simulation instead of transient. Okay, so I'm pressing OK. Now if I select the face, that's not good. Sorry, there was a bug there. I reopened it, and luckily I had all of my design till the last saved, so I'm going to continue the tutorial. So if you open the design and make it right, after you select the magnetostatic, now I'm going to go and select the face and that I want, press F, and then select the face. By the way, now again the air is there, so I'm going to get rid of the air, knowing that it's there, but I'm not going to see it. And now I'm going to select this face, right click on that, assign an excitation. I'm going to say current excitation. If you put voltage excitation, you can have the inductive the capacitance values, but you cannot have the inductance values of this. So go with the current value, the current excitation, which will give you both capacitive or inductive characteristic. So I'm going to go select the current. I'm going to call it, terminal 1 or term 1. The amount of current that you put is basically changing the inductance. For a very small amount of current, you will have some inductance. If you put way more value for the current, it will go higher, and then it'll basically saturate for some value of the inductance. So depending on your application, you put the proper value of the current that you want. I'm going to put 1 amp for this application or for this simulation, just to show you how it works, and then I'm going to press OK. I'm going to go now select the second terminal, right click on that, and on assign excitation, I go under the current and then select that, call that terminal 2, and then say the same amount of current that I put for the terminal 1 with one difference. It's going to be a different direction, and in order to make one of them source and the other sink, we just say swap direction, like this. As you can see, this arrow is changing the direction when I say swap direction. Then press OK. Now I'm going to save it, and look that I have 2 terminals defined like this. And now if I go and run the simulations, I can have all the E and B fields and all the other stuff, and you can calculate your inductance. But one easy way to get your inductance is to right click on parameters and then select under assign, select matrix. Now in the matrix, you say, let's say the source is going to be terminal 1, and then say OK. Okay, since here everything is clear, right click on the parameters, assign a matrix, and then after that select the terminal that you want to be the source, which in this case is terminal 1, and press OK. Done. The other terminal would be by default the sink, so it's not even shown there. Now I'm going to go press on analysis, right click and add a solution type, setup 1, let's name it like that, maximum number of passes 10, percent error 1, whatever, that's okay. These are all the default value that works well. I just want to leave it like that, and then press OK. Save everything, check if there's any error. No, there's no error. Good. Go ahead and simulate. So it's going to start doing the meshing, and after the mesh finished, it's going to run the simulation and electromagnetic simulation is going to run, and after that it's going to give me some good results. So I'm hoping that it's not going to take too long. If it's going to take too long, I'm gonna cut the video and go to the end of this. By the way, one thing that you always want to check is this message manager, and over here you want to make sure that there's no error or some warning or anything. Right now everything is fine here, and it says the adaptive passes did not coverage based on a specified criteria, but now everything is fine. So the warning is not very important here, and normal completion of simulation on server. So that's great. So now we should have some results. To do that, you go on results, right click on create magnetostatic report, and go on data table this time. Okay, press on data table, and now look what we have here. We have coupling coefficients, of course it's 1 because there's just one coil, and we have L for the terminal 1, which is the inductance. We have nominal L for this too. Let's go and just see what would be the inductance of this. So it turns out that the inductance of this coil that we designed was 24 4.37 nanohenry. So now if you go ahead and on the parameters, you on the optometrics, you right click and you say add parametric. You can go ahead and add, you know what, I'm going to change the not the terminal type, but for example the trace width, and I'm going to change it from 0.1 to, let's say, 0.3, and each step is going to be 0.1. Add that there and see the table of variables. Press OK, and then go ahead and analyze the parameters. It's going to run and solve this for two remaining parameters, and after it's solved I will show you the result. Okay, everything is done, the simulation is finished, and now I can go ahead and right click on the result, and now I can have a rectangular plot because now it's a variable, and I'm gonna see the L based on the trace. So the X value is trace and the Y value is the L. So because I have just 3 points here, it's not going to be a very smooth plot, but it's going to be informative enough. So now you can see that the value of the inductance is dropping when you increase the trace width. One reason for that is because when you increase the width, you are basically decreasing the active area in the middle of the inductor, and that will cause to have less flux in the middle, and therefore less d phi t over dt, and basically less inductance. Okay, so that basically concludes my tutorial about how to model and how to simulate a coil and how to find how much inductance it will have. Thank you very much for watching that, and you can like this videos and subscribe to this channel, and also you can leave your comments. I will read them and get back and answer those things. Thank you very much. Have a wonderful day.